Quantum physics is the branch of physics that describes the behavior of very small objects. And here, when I say very small, I mean on the scale of atoms and subatomic particles. There are many properties that arise in quantum physics that don't arise in classical physics. Things operate very differently on the quantum scale than they do at the scale that we interact with normally. Quantum technology makes use of these quantum properties that dictate how things behave at that level. We'll see soon that this can be a very powerful tool. I'll give a quick overview of some of the useful and amazing properties that arise in quantum physics. There are many more than just the three we'll talk about, and each of them could warrant an hour discussion on its own. I'll spare you from such a discussion. To discuss these properties, we first need to introduce the quantum bit. Quantum bits are the quantum version of classical bits, usually just referred to as bits. Just like classical bits are the basic unit of information that classical devices like your phone, your computer, and the internet are built on, quantum bits are the basic unit of quantum information that quantum computers, quantum networks, and the quantum internet are and will be built on. While classical bits and quantum bits are analogous in this way, they're actually quite different in behavior. Quantum bits have many quantum properties that classical bits do not. A classical bit stores one value of information. It either has value 0 or value 1. Quantum bits can be a 0, a 1, or some combination of these two values. When a quantum bit is a combination of 0 and 1, we say it is in a superposition of these two values. Because quantum bits can simultaneously be a 0 and 1, this essentially allows quantum computers to do multiple computations at once. This enables computing speed up for many important problems. When we measure or observe a quantum bit, it collapses into a single value. For example, if my qubit was in a combination of 0 and 1, so a superposition of 0 and 1, and I measured it, and here by measurement, I mean I tested whether the qubit was a 0 or 1, it's going to end up exactly a 0 or exactly a 1. When I measure the qubit in this way, it can no longer be in a combination of these two values. This property is key for quantum security. We can use this property to detect an eavesdropper who intercepts a quantum message, as this is going to change the value of that quantum message. Because of this, we will want to use quantum messages to establish an encryption key to secure our classical information. Qubits can be coupled together in such a way that measuring one qubit will affect the state of the other qubit or even multiple other qubits. This type of coupling is known as entanglement, and we say that qubits coupled in this way are entangled. Something amazing about entanglement is that measuring one qubit will immediately affect the state of the qubit or the qubits it is entangled to, even if these qubits are many light years apart. This is exactly the spooky action at a distance that upset Einstein and many other physicists in the early 20th century. Entanglement is an incredibly important quantum property for quantum technologies. For example, without entanglement, quantum computers would be no faster than classical computers. Entanglement will be vital for almost all of the amazing applications that will be discussed during today's webinar.